This relief valve is the only thing standing between an emergency shutdown and a catastrophic pressure surge. This is known as pressure relief valve or PRV, and it is installed in one of the largest earth-filled dam powerhouse. Because this power station does not have a conventional surge shaft, the PRV plays an important role in protecting the water conveyance system during an emergency shutdown. To all those who don't know what is surge shaft, check this video here, and I'm also attaching the link in description. Now, let's look at the mechanism that controls the turbine wicket gate. This is a coordinated mechanical system. The servomotor or hydraulic actuators push and pull the operating ring, causing it to rotate. This movement is transferred through the connecting rods or links to the wicket gate levers, which are attached to the stem of the individual wicket gates. The lever converts the operating ring movement into opening and closing of each wicket gate. And there is another important safety feature: shear pins or braking members. If a foreign object jams one wicket gate, the shear pin is designed to break, disconnecting that gate from the mechanism and protecting the operating ring and the rest of the wicket gate system from serious damage. Now you can see the joint main inlet valve or MIV for this turbine. This is one of the largest MIVs used in the hydropower industry with a diameter of approximately 10 meters. When the valve is fully open, approximately 460 cubic meters of water pass through it every second. That is 460,000 liters every second, enough to fill an Olympic-sized swimming pool in roughly 5 seconds. I'm going to get close to the MIV and break down and explain as many of its components as I can. At first you may see it as a normal MIV, but when you get close to this thing you can truly see its sheer size. This is the counterweight for the MIV. Just look at the size of the bolts holding this joint valve together. This is the hydraulic cylinder that opens the MIV, and there are two of these. Now, this is the bypass pipe hydraulic valve. Before opening the MIV, the bypass system allows water to fill the space between the MIV and the wicket gates, gradually equalizing the pressure on both sides of the MIV. Once the pressure is sufficiently equalized, the MIV can be opened safely. I've already made a detailed video explaining exactly how this bypass system works, and you can watch it here. These are the air breathers installed on the MIV to allow air to escape during filling and vice versa. We are actually standing on the MIV with the entire flow of water passing beneath us towards the turbine. A massive Francis turbine runner is converting the energy of this water into mechanical power, driving a generator capable of producing approximately 470 megawatts of electricity. There are two bypass pipes installed on this massive MIV, and each one is also equipped with a manual isolation valve. Just look at the size of the MIV counterweights. But closing this valve does not depend entirely on hydraulic pressure. Instead, these massive counterweights provide a fail-safe closing mechanism. If hydraulic pressure is released, gravity takes over and the counterweights drive the valve towards the closed position. Now let's move inside the turbine shaft bit. This turbine shaft is rotating at approximately 107 rpm in a counterclockwise direction. This dial shows the current wicket gate opening. As you can see, the wicket gates are currently 100% open. And this is the speed measuring device which monitors the turbine's rotational speed. And there is also a mechanical overspeed trip or kill switch. If the turbine reaches a dangerous runaway speed, this protection system can initiate the emergency closing of the wicket gate. But when you suddenly reduce the flow of water through a huge turbine, another problem appears. The moving motor has enormous momentum. Stopping or changing that flow too quickly can create a dangerous pressure surge, commonly known as water hammer. And this is where the pressure relief valve becomes extremely important. During an emergency shutdown of this turbine, the PRV opens to provide a control path for relieving the pressure surge and protecting the penstock and water conveyance system. Because this powerhouse does not have a surge shaft, this PRV provides an additional layer of protection against those sudden pressure transients. And before every turbine startup, the system partially opens the PRV up to approximately 20% to verify that it is functioning properly. Now, this small inspection window gives us a view of the turbine guide bearing oil. Back inside the turbine shaft pit, you can see the two indicators again. One shows the wicket gate opening while the other shows the turbine speed. The speed remains essentially constant at around 107 rpm during normal operation, regardless of the electrical load. What changes with the load is the wicket gate opening. When more power is required, the governor opens the wicket gate further, allowing more water to reach the runner. When less power is required, the wicket gate closes partially. And this is the governor hydraulic power unit, or HPU. The system provides the hydraulic power required to operate the wicket gate. These large vessels are hydraulic accumulators. Inside them, nitrogen is separated from hydraulic oil by a piston or a bladder, depending on the accumulator design. They store hydraulic energy and help maintain stable hydraulic pressure. More importantly, they can provide a rapid supply of hydraulic oil when the system needs to move the wicket gate quickly, including during an emergency shutdown or if the main hydraulic pumps are unavailable. And finally, this is the generator circuit breaker, or GCB. When the breaker is closed, the generator is electrically connected to the grid and can deliver its generated power to the transmission system. And right now the GCB is closed and it is delivering 470 megawatt to the national grid. And these are the PRV pipes that we saw at the beginning of the video. And these PRV pipes are right now going through the powerhouse. What looks like a simple valve is actually a critical part of the turbine's protection system, especially in a powerhouse where there is no conventional surge shaft.